Tonight we turn our attention to dark matter, the unseen substance that makes up most of the matter in the universe. This is not science fiction or wild speculation. Dark matter is inferred from careful observations and measurements that reveal the presence of mass we cannot see directly. The evidence comes from multiple independent sources, all pointing to the same conclusion. Most of the matter in the universe does not emit, absorb, or reflect light. We will move through these ideas without excitement or urgency. Dark matter represents a genuine puzzle in science. We know it exists through its gravitational effects, but we do not yet know what it is. This combination of solid evidence and remaining uncertainty is a natural part of scientific progress. We approach this subject with patience and clarity, distinguishing carefully between what observations establish and what remains to be discovered. Before we can discuss dark matter itself, we need to establish what physicists mean by certain fundamental terms. These concepts involve mass, light, gravity, and observation in ways that require careful explanation. Dark matter is matter that does not interact with electromagnetic radiation, with light in all its forms, from radio waves to gamma rays. It does not emit light, does not absorb light passing through it, and does not reflect light that falls on it. This makes dark matter invisible to telescopes that detect electromagnetic radiation. The term dark simply means that dark matter does not interact with light. It is not a statement about colour or visibility in the ordinary sense. It is a statement about physics. Dark matter and light do not interact. This is fundamentally different from the ordinary matter that happens to be dark, like a dark cloud of dust or a planet that does not produce its own light. Dust absorbs and scatters light, which is why we can see dust clouds silhouetted against bright backgrounds. Planets reflect light from their stars, which is how we see them. Dark matter does neither. It allows light to pass through unaffected, except for one crucial effect. It bends light through gravity. Mass is the fundamental property we use to infer dark matter's presence. Mass creates gravitational fields. Gravity affects how objects move and how light travels through space. Even though we cannot see dark matter directly, we can observe its gravitational effects on things we can see: stars, galaxies, gas clouds, and light itself. These gravitational effects reveal that more mass is present than can be accounted for by all the visible matter. When we speak of luminous matter, we mean matter that emits, absorbs, or reflects electromagnetic radiation in some form. This includes stars, which emit light across the spectrum. It includes gas clouds, which absorb and emit light at specific wavelengths. It includes planets and dust, which reflect starlight. It includes all the ordinary matter we can detect through electromagnetic observations. Luminous matter is everything our telescopes can see in any wavelength of light. Observations reveal that luminous matter accounts for only a small fraction of the total mass in galaxies and galaxy clusters. When we measure how fast galaxies rotate, how galaxy clusters hold together, how light is bent by massive objects, and how structures formed in the universe, we consistently find that far more mass is present than we can see. This additional mass, dark matter, is inferred from its gravitational effects. The scale of the discrepancy is enormous. In a typical galaxy, the stars we see contain only about 10 to 20% of the total mass. Dark matter makes up roughly 80 to 90%. In galaxy clusters, the proportion of dark matter is even higher. Across the universe as a whole, ordinary matter, the protons, neutrons, and electrons that make up atoms, comprises only about 15% of all matter. Dark matter comprises the other 85%. The universe is made mostly of something we cannot see directly. Dark matter is not simply ordinary matter that happens to be dark. We can rule out many possibilities for what it might be. It cannot be primarily planets, because planets would have formed from gas clouds that we would see. It cannot be brown dwarfs, failed stars too small to sustain fusion, because we would detect them through their faint infrared glow and gravitational effects. It cannot be black holes in sufficient quantity, because they would cause observable effects we do not see. It cannot be neutrinos, which are known particles, because neutrinos move too fast to produce the structures we observe. Dark matter must be something else. What we know about dark matter comes entirely from gravity. Gravity is the universal force that acts on all mass. Dark matter has mass. So it creates gravitational fields and responds to gravitational fields from other matter. By observing gravitational effects, how objects move, how light bends, how structures form, we can map where dark matter is located and how much of it is present. We can determine many of its properties even without knowing what particles compose it. The distribution of dark matter differs from the distribution of luminous matter. Dark matter forms halos, roughly spherical distributions, around galaxies. These halos extend well beyond the visible edges of galaxies. Dark matter is also distributed throughout galaxy clusters, filling the space between galaxies. On the larger scales, dark matter traces out a cosmic web with dense filaments connecting clusters and voids where little matter of any kind exists. Understanding dark matter requires accepting that we can establish the existence of something without directly detecting it or knowing exactly what it is. This is not unusual in science. Scientists inferred the existence of planets around other stars long before we could image them, based on the gravitational wobbles they caused in their parent stars. We inferred the existence of black holes before imaging them, based on their gravitational effects. Dark matter is similar. The evidence for its existence is overwhelming, even though we have not yet identified the particles that compose it. The search for dark matter's identity continues through multiple approaches. Particle physicists build detectors deep underground, shielded from cosmic rays, hoping to catch rare interactions between dark matter particles and ordinary matter. Astronomers look for signals from dark matter particles annihilating or decaying in space. Theorists propose candidate particles and calculate their properties. The mystery is not whether dark matter exists. The evidence for existence is solid, but what it is. These definitions and concepts form the foundation for understanding dark matter. We cannot see it, but we observe its gravitational effects consistently across many different phenomena and scales. The effects are too large and too consistent to be errors or misunderstandings. Multiple independent lines of evidence all point to the same conclusion. Most matter in the universe is dark matter, and understanding the universe requires understanding this unseen component. To understand how our knowledge of dark matter developed, we must trace the gradual accumulation of evidence over nearly a century. The story shows how an idea that seemed exotic or unnecessary eventually became an essential part of our understanding of the universe. In the 1930s, Fritz Zwicky, a Swiss astronomer working in California, studied the Coma Cluster, a large collection of galaxies about 300 million light years away. Galaxy clusters are gravitationally bound systems. The galaxies orbit within the cluster's gravitational field, much like planets orbit within a solar system's gravitational field. By measuring how fast galaxies move within the cluster, Zwicky could estimate the total amount of the cluster using the virial theorem, a relationship from classical mechanics. Zwicky found that galaxies in the Coma cluster moved much faster than expected based on the visible mass. At those speeds, the galaxies should fly apart unless far more mass was present to hold them gravitationally. He estimated that the cluster contained about 400 times more mass than could be accounted for by visible stars. Zwicky proposed that some form of dunkle materia, dark matter in German, must be present. This result was largely ignored or dismissed. Galaxy clusters were not well understood, and measurements were difficult. Perhaps Zwicky's calculations were wrong. Perhaps some other explanation existed. The idea of vast amounts of unseen matter seemed too radical and unnecessary. For decades, Zwicky's observation remained a curiosity rather than a foundation for new physics. In the 1970s, Vera Rubin and Kent Ford studied the rotation of spiral galaxies. Galaxies rotate, with stars orbiting the galactic center. By measuring the Doppler shifts of light from different parts of a galaxy, astronomers can determine how fast different regions are moving. In a spiral galaxy, some parts move toward us and are blue shifted. Other parts move away and are red shifted. From these measurements, we construct a rotation curve, a graph of orbital velocity versus distance from the center. For a galaxy like the Milky Way, most visible mass is concentrated toward the center. Using Newton's laws and what we know about gravity, we can predict how stars should move at different distances from the center. Near the center, where most mass is located, orbital velocities should be high. Far from the center, beyond most of the visible mass, orbital velocities should decline, following Kepler's laws just as planets farther from the Sun orbit more slowly. Rubin and Ford found that rotation curves do not behave as predicted. Instead of declining at large distances, the rotation curves remain flat. Stars far from the galactic center orbit just as fast as stars nearer to the center. This means that mass continues to be present at large distances, even though we see no stars or gas in those regions. The galaxies must be embedded in large halos of dark matter extending far beyond the visible disks. This was not just one galaxy. Rubin and her collaborators measured rotation curves for dozens of spiral galaxies, and the pattern was consistent. Flat rotation curves were the norm, not the exception. Every spiral galaxy studied showed evidence for dark matter halos. The effect was too large and too consistent to dismiss. Initially, astronomers sought alternative explanations. Perhaps our understanding of gravity was wrong. Perhaps Newton's laws or general relativity needed modification at galactic scales. Perhaps there was ordinary matter we were missing. Cold gas, dim stars, black holes. Each possibility was investigated. Each was found insufficient to explain the observations. Cold gas would absorb or emit light at certain wavelengths, and we can search for these signals. Searchers found some gas, but nowhere near enough to account for the mass discrepancy. Dim stars, or brown dwarfs, would emit faint infrared light and would cause gravitational microlensing of background stars. Surveys set limits on how many could exist, far too few to explain dark matter. Black holes in sufficient numbers would have other observable effects, like disrupting star clusters, which we do not see. By the 1980s and 90s, evidence for dark matter accumulated from many independent sources. Gravitational lensing observations showed that massive galaxy clusters bend light from background galaxies far more than expected from visible mass. Computer simulations of structure formation in the universe could reproduce observed large-scale structure only if dark matter was included. Measurements of the cosmic microwave background showed fluctuations that required dark matter to match theory with observation. The bullet cluster observation in the 2000s provided particularly clear evidence. The bullet cluster is actually two galaxy clusters that collided and passed through each other. During the collision, the hot gas in each cluster, observable in X-rays, interacted and slowed down, remaining behind near the collision point. The galaxies themselves and the dark matter pass through relatively unaffected, since they interact primarily through gravity, which is a long-range force. Gravitational lensing observations of the bullet cluster showed where the total mass is located. The lensing revealed that most mass is not where the hot gas is, but where the galaxies are, offset from the gas. This is exactly what we expect if dark matter exists and pass through the collision with the galaxies, separating spatially from the ordinary matter that interacted and slowed. This observation is very difficult to explain without dark matter. By the early 2000s, dark matter had shifted from a controversial hypothesis to an accepted component of cosmology. Multiple independent lines of evidence, galaxy rotation curves, cluster dynamics, gravitational lensing, cosmic microwave background, structure formation, all converged on the same conclusion. Dark matter is real, it is gravitationally dominant, and it is distributed throughout the universe in predictable ways. Yet we still do not know what dark matter is. We know it exists. We know many of its properties. We know it must be a particle not included in the standard model of particle physics. We know it must interact weakly or not at all with ordinary matter, except through gravity. Identifying the specific particle or particles that constitute dark matter remains at the active area of research. Experiments worldwide search for direct detection, indirect signals, or production of dark matter particles in accelerators. The history of dark matter illustrates how scientific understanding evolves. Early hints were dismissed or overlooked. Accumulating evidence from multiple sources gradually made the case compelling. alternative explanations were tested and ruled out. The framework that includes dark matter successfully explains diverse observations. While we do not yet have all answers, the existence of dark matter is now as well established as many other components of the universe we cannot see directly, like black holes before they were imaged, or exoplanets before they were directly photographed. The evidence is the foundation of knowledge. Dark matter is inferred from multiple independent observations across different scales and using different physical phenomena. Understanding these observations and what they tell us is essential to appreciating why dark matter is considered an established component of the universe. Galaxy rotation curves provide some of the clearest evidence. A spiral galaxy, like the Milky Way, contains hundreds of billions of stars, most concentrated in a central bulge and a flat disk. Gas also resides in the disk. Beyond the visible edge of the disk, very few stars or gas clouds can be detected. If we plot the distribution of luminous matter with distance from the galactic center, it peaks near the center and declines at large distances. According to Newton's laws and general relativity, the orbital velocity of objects in the galaxy depends on the enclosed mass, the total mass within their orbital radius. Near the galactic center, where most visible mass resides, orbital velocities are high. As we move outward beyond the bulk of the visible mass, velocities should decline, following what is called Keplerian decline, similar to how planets farther from the Sun orbit more slowly. Observations show that velocities do not decline. Instead, rotation curves remain flat or even slightly rise at large distances from the galactic center. This means that mass continues to be present at large radii, distributed in a way that keeps orbital velocities constant. The only way to explain this within our understanding of gravity is to have a halo of dark matter extending well beyond the visible disk. The dark matter halo is roughly spherical and contains much more mass than the visible galaxy. This pattern is universal among spiral galaxies. Every well-measured spiral galaxy shows flat rotation curves at large radii, indicating dark matter halos. The ubiquity of the phenomenon argues against it being an artifact or measurement error. Different galaxies at different distances, observed with different telescopes and techniques, all show the same basic pattern. This consistency is powerful evidence. Gravitational lensing provides independent confirmation. General relativity predicts that mass curves space-time, and light follows the curvature. When light from a distant galaxy passes near a massive object, a galaxy cluster, for instance, the light's path bends. The distant galaxy appears distorted, magnified, or even multiply imaged. This is gravitational lensing. The amount of lensing depends on the total mass along the line of sight. By measuring how much background galaxies are distorted, we can infer the total mass of the foreground cluster. These measurements consistently show that clusters contain far more mass than can be accounted for by visible stars and gas. The mass distribution traced by lensing extends beyond the visible matter and is consistent with dark matter halos around individual galaxies and throughout the cluster. Weak gravitational lensing studies hundreds of thousands of galaxies to map the distribution of mass on large scales. These surveys reveal the cosmic web, a network of filaments and nodes where matter is concentrated, separated by voids with little matter. The mass distribution inferred from lensing matches what we expect from dark matter. Without dark matter, we would not see this structure. Galaxy clusters provide another line of evidence. Clusters are the largest gravitationally bound structures in the universe, containing hundreds or thousands of galaxies, along with hot gas that fills the space between galaxies. This gas, heated to tens of millions of degrees, emits X-rays. By observing the X-ray emission, we can measure the gas temperature and density, which tell us about the gravitational potential while holding the cluster together. The gas temperature depends on the total mass of the cluster. Hotter gas requires a deeper gravitational potential well, meaning more mass. When we compare the mass inferred from X-ray observations with the mass we see in stars and gas, there is a large discrepancy. The gravitational mass is typically 5 to 10 times larger than the visible mass. Dark matter is needed to explain the difference. The dynamics of galaxies within clusters also requires dark matter. Galaxies orbit within the cluster's gravitational field. By measuring galaxy velocities, the speeds at which they move, we can estimate the cluster's total mass using the virial theorem. These dynamical mass estimates agree with the X-ray measurements and with gravitational lensing measurements. All three independent methods point to the same total mass, far exceeding the visible mass. The bullet cluster provides particularly clear evidence because it shows spatial separation between dark matter and ordinary matter. Two galaxy clusters collided at high speed. The hot gas in each cluster, which contains most of the ordinary matter, interacted during the collision. Gas particles collided, creating shock waves and friction that slowed the gas, leaving it concentrated near the collision site. The galaxies themselves, being sparsely distributed with large gaps between individual galaxies, passed through the collision largely unaffected. Gravitational lensing observations of the bullet cluster show where the total mass is located. The lensing signal peaks not where the hot gas is, but where the galaxies are, offset by millions of light years from the collision site. This is exactly what we expect if most mass is dark matter that interacts only gravitationally. The dark matter passed through the collision with the galaxies, separating from the ordinary matter that interacted and slowed. This observation is very difficult to explain without dark matter. The cosmic microwave background provides evidence from the early universe. The CMB is radiation from about 380,000 years after the Big Bang, showing tiny temperature fluctuations across the sky. These fluctuations correspond to density variations in the early universe, regions that were slightly denser or less dense than average. Over billions of years, gravity amplified these variations, with denser regions attracting more matter and growing into the galaxies and clusters we see today. The pattern of fluctuations in the CMB depends on the universe's composition. How much ordinary matter, how much dark matter, how much dark energy. Precise measurements of the CMB by satellites like WMAP and Planck allow us to determine these quantities. The results show that the universe contains about 5% ordinary matter, 27% dark matter, and 68% dark energy. The specific pattern of CMB fluctuations could not match observations without dark matter. Large-scale structure formation requires dark matter. Computer simulations, starting from the early universe's conditions and evolving forward in time under gravity, can reproduce the cosmic web of galaxies, clusters, and voids that we observe today. These simulations work only if dark matter is included. Without dark matter, structure does not form quickly enough or with the right characteristics. Ordinary matter alone cannot produce the universe we see. These observations, rotation curves, gravitational lensing, cluster dynamics, the bullet cluster, the cosmic microwave background, and large-scale structure, are independent measurements using different physics and different techniques. They all point to the same conclusion. Dark matter exists. It is roughly 5 times more abundant than ordinary matter, and it is distributed in halos around galaxies and throughout clusters. The convergence of evidence from multiple sources is what makes the case for dark matter compelling. No single observation is conclusive on its own, but together they form an overwhelming body of evidence. While we do not know what dark matter is, observations constrain its properties significantly. Understanding what dark matter must be like and what it cannot be helps guide the search for its identity. Dark matter interacts gravitationally. This is how we detect it. Dark matter creates gravitational fields proportional to its mass, and it responds to gravitational fields from other matter. Gravity is the universal interaction that affects all matter and energy. Since dark matter has mass, it participates in gravity just like ordinary matter. This gravitational interaction is responsible for all the effects we observe. Rotation curves, lensing, cluster dynamics, structure formation. Dark matter does not interact electromagnetically, or interacts so weakly that we cannot detect electromagnetic signals from it. It does not emit light, does not absorb light, and does not reflect light. It is transparent to electromagnetic radiation across the entire spectrum, from radio waves to gamma rays. This is what makes it dark. If dark matter interacted electromagnetically, even slightly, we would see it in some wavelength. Searchers have looked and found nothing dark matter might interact through the weak nuclear force, one of the 4 fundamental forces in nature. The weak force is responsible for certain types of radioactive decay and operates at very short ranges within atomic nuclei. Some theoretical candidates for dark matter particles interact weakly, which is why they are called WIMPs, weakly interacting massive particles. But weak interaction is not required by observations. Dark matter might interact only through gravity. Dark matter must be cold, meaning the particles move slowly compared to the speed of light in the present universe. This is required by the structures we observe. If dark matter were hot particles moving at relativistic speeds, it would stream out of overdense regions instead of accumulating. Simulations with hot dark matter produce structures that do not match observations. Cold dark matter simulations match the cosmic web, galaxy distributions, and cluster properties we see. Neutrinos, which are known particles, were once considered as dark matter candidates. Neutrinos have tiny masses, interact only through the weak force and gravity, and are extremely abundant. However, neutrinos move at nearly the speed of light. They are hot dark matter. The universe with neutrinos as the dominant dark matter does not look like our universe. Structures would be washed out on small scales. This rules out neutrinos as the primary dark matter component. Dark matter forms halos around galaxies. These halos are roughly spherical, extending well beyond the visible disks or bulges of galaxies. The density of dark matter is highest near the galactic center and declines with distance, but not as steeply as the distribution of stars. The rotation curves that remain flat to large radii require this extended halo structure. The exact shape and density profile of dark matter halos are still studied through observations and simulations. Dark matter is collisionless or nearly so. This means dark matter particles do not collide with each other in the way that atoms collide. When two clouds of ordinary matter pass through each other, atoms collide, creating heat and friction. Dark matter clouds pass through each other with little or no interaction. The bullet cluster demonstrates this. The dark matter passed through the collision while the gas did not. If dark matter had significant self-interaction, it would have slowed and remained with the gas. And the amount of dark matter in the universe is well determined. Observations of the cosmic microwave background, combined with measurements of large-scale structure and the expansion history of the universe, constrain the total matter density. About 27% of the universe's energy content is dark matter. Ordinary matter, protons, neutrons, electrons making up atoms, is about 5%. The remainder, 68%, is dark energy, an entirely different phenomenon related to the acceleration of cosmic expansion. Within the matter budget, dark matter comprises about 85% of all matter. This ratio is consistent across different measurements and scales. Galaxy rotation curves show that galaxies are dominated by dark matter. Cluster observations show the same. The cosmic microwave background confirms this at early times. The consistency reinforces that we are observing a real phenomenon with a stable proportion. Dark matter cannot be primarily composed of ordinary baryonic matter, protons and neutrons. Big Bang nucleosynthesis, the production of the light elements in the early universe, constrains the total amount of ordinary matter. The abundances of hydrogen, helium, and lithium produced in the first few minutes depend sensitively on the density of protons and neutrons. Measurements of these abundances match theoretical predictions for a specific baryon density, about 5% of the universe's total energy. There is not enough room in the baryon budget for dark matter to be ordinary matter. MACHOs, massive astrophysical, compact halo objects, such as planets, brown dwarfs, white dwarfs, or black holes, were once considered as dark matter candidates. These objects are made of ordinary matter but do not shine brightly. Surveys looking for gravitational microlensing events, where a macho passes in front of a distant star and briefly magnifies its light, have set strong limits. Machos cannot account for more than a small fraction of dark matter. The halo of our galaxy is not made of dark planets or failed stars. Theoretical candidates for dark matter particles come from extensions to the standard model of particle physics. WIMPs are one class arising naturally in supersymmetric theories. Axions are another class, originally proposed to solve a problem in quantum chromodynamics, the theory of the strong nuclear force. Sterile neutrinos, heavier cousins of ordinary neutrinos, are a third possibility. Each candidate has different properties and would require different detection methods. Despite decades of searching, no dark matter particle has been conclusively detected. Direct detection experiments, deep underground, to shield from cosmic rays, wait for rare collisions between dark matter particles and atomic nuclei. Indirect detection experiments look for signals from dark matter particles annihilating or decaying in space. Collider experiments at facilities like the Large Hadron Collider search for dark matter production in particle collisions. So far, no experiment has found definitive evidence for dark matter particles. The non-detection does not undermine the evidence for dark matter's existence. The gravitational effects are observed and well measured. What we lack is knowledge of the particle identity. This is a common situation in science. We know black holes exist from their gravitational effects long before we understood their formation or properties in detail. We knew atoms existed before we understood their structure. Dark matter is similar. Its existence is established by evidence, while its nature remains to be discovered. Constraints on dark matter's properties narrow the search. We know it must be massive enough to be cold in the current universe. We know it must have low or zero electromagnetic interaction. We know it must be collisionless or nearly so. We know it cannot be ordinary matter. These constraints guide both theoretical proposals and experimental searches. With each experiment that sets limits, the parameter space for possible dark matter particles shrinks, bringing us closer to an answer. Understanding dark matter in concrete terms requires examining specific observations in detail and seeing how dark matter explains what we see. These examples illustrate both the phenomena dark matter is invoked to explain and the consistency with which dark matter provides answers. Galaxy rotation curves can be examined for a specific galaxy to see the discrepancy clearly. Consider the Andromeda galaxy, our nearest large galactic neighbour, located about 2.5 million light years away. Andromeda is a spiral galaxy similar to the Milky Way. Astronomers have measured the rotation curve by observing the Doppler shifts of hydrogen gas at different distances from the centre. Near the galactic centre, within about 10,000 light years, the rotation velocity rises steeply. This is expected because most of the visible mass stars in the central bulge is concentrated here. Beyond this, in the disk where spiral arms reside, the rotation velocity should begin to decline as we move past most of the mass. If only visible matter were present, velocities should drop following a Keplerian curve, decreasing proportionally to 1 over the square root of distance. Instead, the rotation curve flattens around 30,000 light years from the center and remains roughly flat out to at least 100,000 light years beyond the visible edge of the galaxy. At these distances, velocities are around 200 kilometers per second, similar to velocities closer in. This means that mass continues to be present at large radii, even though we see few stars or gas clouds there. To explain this flat rotation curve, we require a dark matter halo, with mass increasing roughly linearly, with distance from the center out to large radii. The halo extends perhaps 300,000 light years or more from the center, much larger than the visible galaxy. The total mass of the dark matter halo is several times larger than the mass of all visible matter, stars, gas and dust, in Andromeda. This is the pattern seen in every spiral galaxy with measured rotation curves. Gravitational lensing by galaxy clusters can be examined through examples like Abell 1689, a massive cluster about 2.2 billion light years away. Abell 1689 contains hundreds of galaxies and vast amounts of hot gas observable in X-rays. Light from galaxies far behind Abell 1689 passes through the cluster and is bent by the cluster's gravity. The background galaxies appear as distorted arcs and multiple images around the cluster. By measuring the positions and shapes of these lensed background galaxies, astronomers can reconstruct the mass distribution in Abell 1689. The analysis shows that the cluster contains about 2 million midbillion solar masses within its central regions. Of this total mass, only about 1% is in stars within the galaxies. About 10 to 15% is in hot gas detected through X-rays. The remaining 85 to 90% is dark matter, inferred from the lensing but invisible in any wavelength. The dark matter distribution in Abell 1689 is smoother and more extended than the distribution of galaxies or gas. It forms a large halo encompassing the entire cluster, with the density highest at the center and declining outward. This distribution is consistent with what simulations predict for dark matter in clusters. The lensing provides a direct measure of where the total mass is, showing clearly that most mass is not where the visible matter is. The Bullet cluster, officially known as 1E0657-56, provides one of the clearest visual demonstrations of dark matter. This system consists of two galaxy clusters that collided at speeds of about 4,000 kilometers per second. The collision occurred roughly 150 million years ago, and we see the aftermath. One cluster passed through the other, and they are now separating. During the collision, the hot gas in each cluster, hundreds of trillions of solar masses of material heated to tens of millions of degrees, interacted through electromagnetic forces. Gas particles collided, creating shock waves visible as bright regions in X-ray images. The interaction created drag, slowing the gas. Most of the gas remained near the collision site, between the two clusters as they separate. X-ray observations show two concentrations of hot gas slightly offset from each other, marking where the clusters collided. The galaxies themselves, being widely spaced with large gaps between them, pass through the collision with little interaction. Each galaxy in one cluster passed between galaxies in the other cluster, continuing mostly undisturbed. The galaxies are now found further from the collision site than the gas, having continued moving while the gas slowed and stayed behind. Gravitational lensing observations show where the total mass of the system is located. The lensing signal is strongest, not where the hot gas is, but where the galaxies are, about 1.5 million light years offset from the gas concentrations. This indicates that most mass passed through the collision with the galaxies. Since the galaxies themselves contain only about 1% of the cluster's mass, and the gas contains about 10%, the remaining 89%, dark matter must be located with the galaxies. This spatial separation between dark matter and ordinary matter is exactly what we predict if dark matter exists and interacts only gravitationally. The dark matter halos of the two clusters pass through each other just like the galaxies, since dark matter does not collide with itself or interact electromagnetically. The ordinary matter, in the form of hot gas, interacted and stayed behind. The observation is difficult to explain without dark matter. Simulations of structure formation illustrate how dark matter shapes the universe. These simulations begin with conditions in the early universe shortly after the Big Bang, when matter was distributed almost uniformly with tiny fluctuations. The simulations evolve forward in time using gravity, computing how matter clumps under its own gravitational attraction. Simulations that include only ordinary matter do not produce structures matching observations. Ordinary matter remains coupled to radiation until about 380,000 years after the Big Bang. During this time, radiation pressure prevents matter from clumping efficiently. By the time matter decouples from radiation, not enough time remains for structures to grow to the sizes we observe. Galaxies and clusters form too late and are too diffuse. Simulations that include dark matter match observations. Dark matter, not interacting with radiation, begins clumping earlier. By the time ordinary matter decouples from radiation, dark matter has already formed gravitational potential wells. Ordinary matter falls into these wells, speeding up structure formation. Galaxies form at the right times, in the right numbers, with the right sizes. The cosmic web of filaments and voids matches what large galaxy surveys observe. These simulations are sophisticated, tracking billions of particles representing dark matter and ordinary matter, including the effects of gravity, gas pressure, star formation, and feedback from supernovae and black holes. The simulations successfully reproduce the universe we see, but only when dark matter is included. Without it, the simulated universe looks nothing like reality. In our own Milky Way, dark matter affects stellar motions in measurable ways. The Sun orbits the galactic center at about 220 kilometers per second, taking roughly 230 million years to complete one orbit. This orbital speed depends on the total mass within the Sun's orbit. Most of this mass is dark matter. If the Milky Way contained only visible matter, the Sun should orbit more slowly. Stars high above or below the galactic plane, in the halo of the galaxy, have velocities that constrain the local dark matter density. Measurements of these stars' motions allow estimates of how much dark matter is present near the Sun. The local dark matter density is about 0.3 solar masses per cubic parsec, equivalent to roughly 1 dark matter particle per few cubic centimeters if the particles have typical WIMP masses. This density is small by terrestrial standards, but significant on astronomical scales. These detailed examples, Andromeda's rotation curve, Abell 1689's lensing, the bullet cluster's separation, structure formation simulations, and local Milky Way constraints, all demonstrate how dark matter provides consistent explanations for diverse observations. The dark matter hypothesis is not invoked to explain a single anomaly. It explains a wide variety of phenomena across many scales, and the amount and distribution of dark matter required to explain each phenomenon are consistent with each other. This consistency across independent observations is the hallmark of a correct scientific explanation. Dark matter connects to multiple areas of physics, from particle physics to cosmology, influencing how we understand the universe's composition, evolution, and ultimate fate. Particle physics is intimately connected to the dark matter problem because dark matter must be composed of particles not included in the Standard Model. The Standard Model successfully describes ordinary matter, quarks forming protons and neutrons, electrons orbiting nuclei, neutrinos produced in nuclear reactions, photons carrying electromagnetic force. The Standard Model is one of the most successful theories in physics, tested to extraordinary precision. But it does not include dark matter particles. This means that physics beyond the Standard Model is required. Discovering dark matter would be direct evidence for new physics. Theoretical extensions to the Standard Model naturally produce dark matter candidates. Supersymmetry, a proposed symmetry between matter particles and force-carrying particles, predicts a new set of particles, some of which could be dark matter. The lightest supersymmetric particle, if stable, would be an excellent dark matter candidate. Axions arise from attempts to solve the strong CP problem in quantum chromodynamics, the theory of the strong nuclear force. The axion is a hypothetical particle with very small mass and very weak interactions. If actions exist with the right properties, they could account for dark matter. Unlike WIMPs, actions would be very light and extremely abundant. Detecting actions requires different experimental techniques than detecting WIMPs. Direct detection experiments aim to observe dark matter particles colliding with ordinary matter. These experiments use ultra-pure materials, typically liquid xenon, liquid argon, or cryogenic crystals. instrumented to detect the tiny energy deposits from rare collisions. The experiments are located deep underground to shield them from cosmic rays that would create overwhelming background signals. Experiments like Lux, Xenon, Panday X and others have set increasingly stringent limits on WIMP interactions. So far, no conclusive detection has been made. Indirect detection searches for signals from dark matter particles annihilating or decaying in regions where dark matter is dense, such as the centers of galaxies or the Sun. When dark matter particles collide and annihilate, they should produce ordinary particles, photons, neutrinos, or matter-antimatter pairs. Telescopes observing gamma rays or neutrinos from these regions search for excess signals that could indicate dark matter. Some observations have shown interesting anomalies, but none have been confirmed as dark matter signals. Collider experiments at the Large Hadron Collider search for dark matter production. If dark matter particles are not too heavy, they might be produced in high-energy proton collisions. The dark matter particles would escape the detector unseen, but their presence would be inferred from missing energy and momentum in the collision. Searchers have looked for such signatures, finding nothing conclusive but constraining the properties of possible dark matter particles. Cosmology relies fundamentally on dark matter. The standard cosmological model, lambda CDM, lambda cold dark matter, includes dark matter as an essential component. Lambda represents dark energy, the mysterious component causing the universe's expansion to accelerate. CDM is cold dark matter. This model successfully explains the cosmic microwave background large-scale structure, the expansion history of the universe, and numerous other observations. Without dark matter, cosmology cannot explain observations. The cosmic microwave background fluctuations require dark matter to match the observed pattern. Structure formation requires dark matter to produce the cosmic web. The abundance of galaxy clusters at different times in cosmic history requires dark matter. Cosmology provides some of the strongest evidence for dark matter's existence. Even though cosmology cannot tell us what dark matter particles are, the ultimate fate of the universe depends partly on dark matter. If the universe's expansion continues accelerating due to dark energy, as current observations suggest, galaxies outside our local group will eventually recede beyond our observable horizon. Stars will eventually burn out, and the universe will become cold and dark. Dark matter will persist, its particles continuing to orbit in galactic halos long after stars have died. On unimaginably long timescales, if dark matter particles can decay or annihilate, even the dark matter may eventually disappear. Modified gravity theories represent an alternative approach to the dark matter problem. Instead of invoking new particles, these theories propose that our understanding of gravity is incomplete or wrong on galactic scales. Modified Newtonian dynamics, or MOND, is one such proposal. MOND modifies Newton's laws at very low accelerations, such as those experienced by stars in the outer regions of galaxies. With appropriately chosen modifications, MOND can explain galaxy rotation curves without dark matter. However, modified gravity theories struggle to explain other observations. The bullet cluster is particularly challenging for MOND because it requires spatial separation between gravitational mass and visible matter, which is difficult to achieve by modifying gravity alone. The cosmic microwave background and large-scale structure also present problems for modified gravity. While MOND remains an active area of research, most physicists consider dark matter a more successful explanation for the full range of observations. The interplay between dark matter and ordinary matter influences galaxy formation. Dark matter provides the gravitational scaffolding. Dark matter halos form first, creating potential wells. Ordinary matter falls into these wells, accumulating in the centers of halos. Gas cools and condenses, forming stars. The stars form galaxies. Without dark matter, this process would be too slow to produce the galaxies we see in the time available since the Big Bang. Feedback processes complicate the picture. Supernova explosions and radiation from massive stars heat and expel gas from galaxies. Black holes at galactic centers accrete matter and release enormous energy, affecting star formation throughout the galaxy. These processes operate on ordinary matter, but are influenced by the dark matter distribution. Understanding galaxy formation requires understanding both dark matter and these complex baryonic processes. Dark matter research exemplifies the interconnectedness of physics. Particle physics provides candidate particles and detection methods. Astrophysics provides observations and constraints. Cosmology provides the large-scale context. Each field contributes pieces of the puzzle. Progress requires collaboration across disciplines, combining theoretical insights with observational campaigns and experimental searches. The mystery of dark matter's identity remains, but the combined efforts of these fields continue to narrow the possibilities and refine our understanding. As we move towards the close of our discussion, we can restate gently some of the central ideas we have explored. Dark matter is matter that does not interact with light. It does not emit, absorb, or reflect electromagnetic radiation. We cannot see it with telescopes that observe light in any wavelength. Yet we know dark matter exists because we observe its gravitational effects on things we can see. Stars and galaxies move in ways that require more mass than visible matter provides. Light from distant galaxies is bent by gravity from unseen mass. Galaxy clusters contain far more mass than can be accounted for by stars and gas. These observations are not isolated anomalies. Galaxy rotation curves have been measured for thousands of galaxies, showing consistently that dark matter halos extend well beyond visible disks. Gravitational lensing observations map the mass distribution in hundreds of galaxy clusters, consistently showing that most mass is dark. The cosmic microwave background from the early universe shows fluctuations that require dark matter to match theory with observation. Large-scale structure formation simulations produce realistic universes only when dark matter is included. The evidence comes from multiple independent sources using different physical phenomena. The convergence of evidence from rotation curves, gravitational lensing, cluster dynamics, the bullet cluster collision, the cosmic microwave background, and structure formation is what makes the case for dark matter compelling. Each line of evidence might have alternative explanations, but together they form a consistent picture that dark matter provides. Dark matter makes up about 27% of the universe's total energy content. Ordinary matter, the atoms that form stars, planets, and us, comprises only about 5%. Within the matter budget, dark matter is roughly 85% of all matter. This proportion is consistent across different observations and scales. The universe is made mostly of something we cannot see directly. We know many things dark matter cannot be. It cannot be ordinary matter like planets, brown dwarfs, or black holes in sufficient quantity. Observations rule out these possibilities. It cannot be neutrinos, which move too fast to produce the structures we see. It cannot interact significantly with electromagnetic radiation, or we would see it. It must be cold, meaning particles moving slowly in the present universe. It must be collisionless, or nearly so, passing through itself during cluster collisions. What dark matter remains unknown. Theoretical candidates include WIMPs, weakly interacting massive particles arising naturally in supersymmetric theories. Axions are another possibility, originally proposed to solve a different problem in particle physics. Other candidates exist in various theoretical frameworks. Despite decades of experimental searches using direct detection, indirect detection, and particle collider production, no dark matter particle has been conclusively identified. This lack of identification does not undermine the evidence for dark matter's existence. We establish existence through observed effects. Black holes were inferred from gravitational effects long before we understood them fully. Atoms were known to exist before their structure was discovered. Dark matter is similar. The gravitational evidence for its existence is overwhelming, even though we have not yet identified the particles that compose it. Modified gravity theories attempt to explain observations without invoking dark matter by changing our understanding of gravity on large scales. These theories have successes, particularly in explaining galaxy rotation curves, but they struggle with other observations like the bullet cluster, where dark matter and ordinary matter are spatially separated, and the cosmic microwave background, which requires specific matter densities to match observed fluctuations. Most physicists consider dark matter a more successful explanation for the full range of evidence. The search for dark matter particles continues through multiple experimental approaches. Direct detection experiments deep underground wait for rare collisions between dark matter particles and ordinary matter. Indirect detection searches look for signals from dark matter annihilation or decay in space. Particle colliders search for dark matter production. Each experiment that sets limits narrows the possibilities, bringing us closer to discovering dark matter's identity. Understanding dark matter is essential for understanding the universe. Dark matter dominates the mass budget. It shaped structure formation. It holds galaxies together. It influences the cosmic web. Without dark matter, we cannot explain the universe we observe. The mystery is not whether dark matter exists, the evidence is solid, but what it is. This is a natural state for science, where We establish phenomena through observation and continue searching for deeper understanding. We have moved through these ideas slowly, examining the evidence carefully and distinguishing between what is observed, what is inferred, and what remains unknown. Dark matter represents a genuine scientific mystery being actively investigated. The evidence for its existence comes from multiple independent sources and is consistent across scales. The search for its identity continues, guided by observations that constrain its properties and experiments that test theoretical predictions. We have now travelled through the essential concepts of dark matter, how it reveals itself through gravitational effects, how multiple independent observations point to its existence, what properties it must have, and what remains to be discovered about its identity. We have seen that dark matter, though unseen, is as firmly established as many other components of the universe we have inferred indirectly. There is no need to retain every detail. Dark matter involves concepts about mass, gravity, and observation that take time to fully appreciate. Understanding develops through patient attention to evidence. You may have drifted in and out as we spoke, and that is entirely natural. Each section we discussed was intended to stand on its own, so that wherever your attention rested, you encountered ideas that were complete in themselves. The universe contains more than meets the eye. Most of the matter around us, holding galaxies together and shaping the cosmos, is invisible. Yet through careful observation and measurement, we can infer its presence, map its distribution, and constrain its properties. This ability to establish existence without direct detection exemplifies how science works. Building knowledge through evidence, testing hypotheses against observations, and distinguishing between what we know and what we have yet to discover. We close gently, without urgency, as we began. The concepts we explored are grounded in extensive observations across many scales and phenomena. Dark matter is one of the major unsolved problems in physics, yet its existence is well established. The search for its identity continues. The mystery invites curiosity without demanding answers tonight.